Okay, very good. So listen, I've been teaching at Princeton University for 39 years. My work began in early 1980s with the deregulation of trucking with truckload trucking. And truckload was one of these great problems that introduced me to the challenges of dealing with decision and uncertainty. Now, over my career, I ended up spanning a whole wide range of problems that I've pulled together on this slide. And whether it's supply chain management, energy, health, e-commerce, logistics, it's a wide range of problems, but it all started with truckload trucking, and it has ended with truckload trucking with the starting of optimal dynamics, which is very exciting to me. Now, a lot of what goes on in these problems is there's a lot of information flowing through. And then you have people making decisions. Now, these are all transportation companies, and you have these rooms full of computers with a lot of data and people making decisions. Uh, uh, Now, a lot of this is very much like a Tesla manufacturing line, where just as we have information moving down and then people act on it with decisions, in a manufacturing line, you've got car chassis moving down with robots acting on it to eventually make a car. I think we need to start looking at the general area of making of information decisions similar to an automotive assembly line. Now, we make decisions to maximize a number of goals and objectives, and whether it's increasing profits, reducing costs, uh, improving employee retention, which is a big deal in the trucking industry, maximize productivity, or maybe we're pressured to reduce our carbon footprint. There's a large number of goals. Now, how we improve performance is by making better decisions. So here's an interesting first question. What decisions are you making? It's a little surprising how many companies where you can say they really want to work better, but if you ask them, what decisions are you making, they sort of stare at you blankly. Sort of the idea is, well, we sort of already know that. But I think you actually really have to make an explicit list. These are the decisions. And then you have, okay, now that I've listed my decisions, how do we make effective decisions? Somebody in the room is going to say, we need to turn to artificial intelligence. Now, artificial intelligence is really an umbrella term. A lot of people today say, oh, it's really AI is like machine learning. Really, it's anything that has computers acting intelligence, and maybe they're behaving like humans. But increasingly, we want computers that are smarter than humans. 1960s and 70s, it was a lot of rules. But it didn't scale to the more complex problems. When we got to the 1990s, optimization came rolling in, and that was a big excitement because it was a major new technology, couldn't handle uncertainty. Early 2000s, the new AI became neural networks, image recognition, pattern recognition, voice recognition. And that's still true today. People often will use the term AI, and what they really mean is machine learning. Now, many of you, maybe not all, will have started hearing about reinforcement learning. So this started to hit the lay press circa 2015. This is when we started to have computers optimizing chess or computer Go and optimizing robots. So 2020 and onward, what's the next generation? Now, we can think of 5 layers of intelligence, and it all starts with you have to know the state of the world. This is bar charts and QR plots and voice recognition and image recognition. Then you have communication, where you have to tell people and share information. Finally, you get to transactions execution. This is ERP systems and transportation management systems. This is where you get the rooms full of computers, computer screens with people sitting and making decisions. I'm going to jump all the way up to learning. This is the first layer where you really think of computers as being intelligent. Now, there's roughly four types of learning. Pattern matching. Is it a flower? What is the person saying? What is the email asking for? You have classification. What product should I recommend for this customer? What treatment should I recommend for a patient? Inference, how will an increase in price affect market demand, or what's the condition of a piece of equipment? And then good old-fashioned prediction. Here's the history of prices or weather, or customer demands, what will happen in the future. Now, whatever you do with machine learning, you're drawing on 3 classes of computer models. Lookup tables, if it's cold, wear a coat. Parametric models, if you raise the price, the demand goes down. And non-parametric models are just locally parametric models that can fit almost anything. Now, if you've heard of neural networks, you're wondering, well, wait a minute, where are neural networks? It turns out they're here. They sort of sit between parametric models and non-parametric models. Uh, Simpler neural networks are considered parametric, but if you hear about deep neural networks, it's really a form of non-parametrics. Now, let me show you a little bit of math. And every now and then, for those of you who come from business or the executives and managers, occasionally I'm going to show a little bit of math, but it's not going to last. I will always link this back to real business problems. But I'm going to start with showing you what machine learning looks like. So this means coming up with a function. Let's say the function has to predict demand as a function of price. So somebody comes in and says, I think it's a linear function. This actually happened to me with an e-commerce problem with hotel revenue management. And of course, if I think it's a linear function, I want the best linear function. Now, somebody else may come in and go, no, 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 no. It's got to be a nonlinear function like this S-curve. Fine, I'll live with that. Let's do the best version. Now, nowadays, somebody is going to come in and go, oh, you've got to use a neural network. And my only word of caution is neural networks are very high dimensional. They can fit almost anything, which means they can fit noise. But whatever it is, it's going to be one of these three classes of functions: the lookup tables, the parametric models, the non-parametric. And when we're looking for the best statistical model, somebody, usually a human, has to come in and say, I'm going to look at this class of model. And then a computer will come in and say, oh, but you've got a lot of tunable parameters. Here, I will use a big data set to fit the model to these observations. And you need a training data set. Now, let's go to that fifth layer, decisions. Now, decisions come in many flavors. Every one of these problems involves a physical process with people making decisions. Behind every one of these is some type of decision. Now, you don't need to read all of these, but every single box is a question implying a decision that has to be made for the picture that was behind the box. Now, there are really three broad types of decisions: decisions that impact physical resources, financial decisions, and informational decisions. The physical decisions can be managing inventories, assigning drivers and moving trucks, scheduling nurses. Financial decisions can be pricing, insurance, managing investments, or hedging contracts. And informational decisions, I may want to send information. May want to share something, say, with a vendor. Marketing and advertising is a form of collecting information, running experiments, whether it's in the lab or the field, and testing new drugs. Now, there's a number of time frames as well. Strategic planning and design is when you're simulating operational decisions, but in the future, like how many drivers should a company have, which lane should a carrier serve, and what policies to use for getting drivers home. Tactical planning decisions are decisions you make now that affect the future, but not the distant future, more the near term. What load should I accept, or what commitment can you give to a driver to get home? Or what brokerage should a carrier call to move a load externally? And then you have the real-time execution decisions. What driver should be assigned to a load right now? Where should the load be relayed, for example? And maybe what spot price should a carrier accept for a load? You can think of the strategic planning decisions as where we need to simulate decisions in the future, but they don't depend on the state of the system now. Tactical planning, I'm still just simulating decisions in the future, but it does depend on the state of the system now. The real-time execution decisions is I absolutely depend on the state of the system now, and I may need to simulate decisions in the future to understand the impact of a decision made now. Now, you also have decisions made at different levels of the organization. You have the C-suite. Typically, these would be strategic planning decisions. You can have various levels of middle management, inventory planning, pricing, staffing, and equipment decisions, setting performance metrics. And then, of course, you have the field operations, which is where you're actually dispatching the trucks or scheduling machines. Now, we've heard about optimization. Deterministic optimization, we use it every day when we use our navigation systems. We want to find the best path to a destination. Or maybe a more complex problem is to locate facilities, which I'm doing in a strategic planning system. One of the big breakthroughs was using optimization, and that's that fancy math there in the middle. And you hire anybody with a background in math programming from anywhere in the world, they speak that language. And the people who've learned that language can go to a complex operation like an airline, translate that physical system into this math, go to a computer package, and out comes an airline schedule. Every major airline uses these packages today. Now, let's go back to my range of problems. And once again, behind every one of these problems is a decision. But after you make every one of these decisions, you get new information. And this is the information that arrives after you make the decision. It's relevant to the decision. I would have liked to have known it, but I have to make the decision before this becomes known. So these are sequential decision problems. And this is what describes most settings. So you have decision, then new information comes in. You make another decision, now more information comes in. So an inventory planning decision, I can make a decision to order inventory, and maybe it arrives right away in e-commerce, but maybe it arrives days or months into the future if it's coming from China. Then I observe the demands for that product. Now I make other decisions in the future. Now I observe more demands, so on and so forth. If I'm in the trucking company, I've got sequences of assigning drivers to loads over time. I also have other decisions like accepting which loads to make commitments to and what prices to charge and how to route drivers home. Now, the problem with sequencing decisions and information is, let's take a really simple problem. I just have to buy, sell, or hold an asset. So I take what I know now, and I have this simple buy, sell, or hold decision, and after which the price can go up, down, or stay the same. And then I have another decision, and then more information, another decision. This is a trivial problem, and it gets immensely complicated if I just look out a few time periods. So this is the complexity of intermingling decisions with new information. So back to a little bit of math, we can take any one of these sequential decisions and break it down to what we call the state at time t, which is what we know. This is the information that we know or believe, because there may be things that I don't know perfectly. Then I make a decision, and it can be buying or selling an asset, accepting a load, or dispatching hundreds of drivers to hundreds of loads. It can be very complex decisions. Then I have this new information that arrives after I make the decision, and so on and so forth. Each time I make a decision, I get some sort of contribution or incur a cost, depending on your perspective. It depends on what I know, could depend on prices and the decision. Decisions are made with a method that we're going to call a policy. There's many ways of calling this, but that's what we're going to call it. Every time I use the word policy, it's some method for making decisions. And my goal is to find the best method. So I want to maximize expectations. Now, modeling these sequential decision problems is actually something that the academic community is quite confused about. I can name 15 different communities with 8 fundamentally different notational systems and a host of different languages and methods and problem classes. On the left-hand side, whether or not you're a mathy type, there's 5 dimensions, 5 bits of mathematics that describe every sequential decision problem. The state variable, which consists of maybe the physical state like inventories, other information like prices and weather, and a belief state, which is beliefs about things I don't know perfectly, like the future, or where is a truck driver, or where is my shipment. You have decision variables depending on your community, comes in different flavors. I like to use X. The exogenous information is new information that once I make the decision, things come in from outside the system. I call that capital W. Transition function simply says this is how the state variable evolves over time. And now we're back to the problem of making decisions. Now, going from modeling to the real world, modeling is critical if you want to put a problem on the computer. Okay, if you want to say, hey, let's use AI, which means let's use the computer to help me out, you're going to have to do mathematical modeling. But I would also claim that modeling helps you think about a problem. So I'm sure almost everybody from the business side has sat down to say, how do we solve this problem? And it's complicated. And they all get around a table and argue, and it's fairly unstructured thinking. Computers can't handle unstructured thinking. It has to be very explicit. So a computer will teach you how to think about a problem, and it'll teach you the things that you have to put together. Now, I want to illustrate a lot of this in the context of truckload trucking. Now, of those 5 elements, there's 3 that are really important. What performance metrics are you focusing on? What decisions are involved? What are the sources of uncertainty? These are the big 3 modeling elements that we have to get through. Performance metrics. Now, if you work at any sort of a reasonable sized company, there's a lot of these. Of course, we want to maximize profits. But we've got fixed and variable costs, we've got revenues, and then down below there we have all sorts of things. So in trucking, we have metrics related to loads like revenue per mile, driver metrics like productivity and getting drivers home and driver retention and turnover. And then metrics related to the network and equipment metrics and back office metrics. You can have hundreds of these metrics. We need to recognize that they're all there in varying degrees of importance. Now, decisions, as I said before, they come in strategic, tactical, and real time. We need to sit down and list these. And by the way, not only do we list strategic, tactical, and real time, we should also have a thought as to who's making the decision, who owns the decision. So we need to get our list of decisions down. And finally, the information processes. These are the sorts of uncertainty. So after I make a decision, what information becomes available? Well, there's a lot of information flowing in the business world. You've got information from the shippers, like new orders booked. You've got information from drivers. Will they accept the assignment of a load? The drivers that will quit, or drivers that have just hired onto your company. You have things going on in the market like spot prices, and then you've got that network with, weather delays and travel times. Now, I want to say something about a state variable. State variables sound very geeky. People who come from business will hear the word state variable. By the way, I can tell you, even the academics don't understand what a state variable is. It's really kind of funny. In a nutshell, it's very simple. It's all the information you need to make a decision. Now, that sounds very simple, but I will tell you, when you sit down to make a computer make a decision, you know exactly what information he needs. When you watch a human making a decision and say what information you need, you get something very fuzzy. Now, the human decision maker may say, well, I really need, say, a forecast. But if that's expensive or time consuming, that person's manager may come in and go, look, just get the job done, stop whining. And so this happens quite a bit. And it's particularly problematic with people in an operational setting. Trust me, build a computer model. Even if you don't build it, even if you think about it, we will be able to come in and say, and here's exactly the information a computer model would need. So probably it's the information a human would need as well. So state variables allows you to articulate what you need in clear, unambiguous language. And I've actually worked at companies where I think the single biggest impact was we figured out what information they need and we built those core tools. Now, modeling at this point, once you've got those basic things done, there's a bunch of technical steps I am not going to go into. But once you go through them and formulating all your notation and variables and implementing on the computer, we now have a complete model and face the problem of designing those policies, those methods for making decisions. So here, there are three places where we have the policy being a method for making a decision. And often I get people saying, what do you mean by that? What is a policy? Even academics will ask this. A policy is a method that makes a decision using the information in the state variable. Any method. So far, I have found about 45 words in the English language that effectively mean the same thing as policy. And if you think that you have a 46th word, go to tinyurl.com, policies and decisions, and add it to the spreadsheet there. We're going to just use the word policy, but every time I say that word policy, just means some method for making decisions. Now, it turns out there's two fundamental methods for making decisions, for designing policies. One is what we call the policy search class, where we just look within a class of functions to find the one that works best. And the second has to do with approximating the future. So let's just start off with the first one. I'm going to divide this into two subclasses. The first I call policy function approximations. These are the simple rules. Buy low, sell high, order up to inventories. The inventory goes below, order up to another level. A policy function approximation could be any rule, any lookup table, linear, nonlinear models. It could be a neural network. If it's cold, wear a coat. This is how we humans get by most of our decision making, is with a PFA. Now, the second class of policy search method, I call it a cost function approximation. Now, this is a term I've introduced. It actually is widely used in industry. Hasn't gotten really any recognition from the academic community. This is where you solve a simplified optimization problem, but then you put in tunable parameters. So imagine that you're trying to find the best path to a destination so that you can figure out what time to leave so that you arrive for your appointment. And Google Maps comes back and says, it's going to take 40 minutes. fine. I'm okay with the path. But that 40 minutes, I really want to make sure I arrive on time. And I know that there's congestion. So maybe I'm going to add in 15 minutes. That's a tunable parameter. And if I do this trip over and over again, I'll learn whether that 15 minutes is too much or too little. Assigning a driver to the closest load, but I may put in penalties for missed delivery appointments. That third one, there's an equation that's actually widely used at Google and Facebook. I want to find an ad that gets the most ad clicks, or I want to advertise a product that gets the most revenue. And I have an estimate of the revenue. That's the estimated for product X, but that estimate may not be very good. And in fact, I maybe have had some bad luck, and the estimate is lower than what it really should be. So we're going to add in what we often call an uncertainty bonus. We're going to take the standard deviation of that estimate. Now imagine your bell-shaped curve. You have the mean and you have that standard deviation. And then we're going to multiply that standard deviation by a tunable parameter theta. Now what I have to do is tune theta. This is widely used in the tech sector to help figure out what to post on the internet. Now, both PFAs and CFAs have tunable parameters. That's what happens in the policy search class. And you may have one tunable parameter, you may have several, you may have hundreds. But generally now I have to tune them. And generally what we'll do is we'll say, hey, let's take a guess at two elements, see how it works. But at that point, I'm going to get a noisy estimate. So now I have to figure out, how do I search over the thetas? You can search in a simulator. So Optimal Dynamics has spent thousands of hours and many years in my academic lab tuning its truckload fleet simulator. There are times when you simply have to tune things in the real world. Now, the second class of policy is based on what we call look-ahead approximations. And just as the policy search class divides into two subclasses, the same is true with look-ahead approximations. Now, look-ahead approximations means I have a choice, and I look at the immediate cost or contribution of that choice, but then downstream, I have other things happening. I have to look off into the future. Okay, take a deep breath. Yes, we have to deal with this, unfortunately, very ugly piece of mathematics, but that's the contribution of what we receive now, and that's all the downstream stuff. So you just have to realize, okay, there's how much money I make or cost I incur, and then there's all that stuff in the future where I have to deal with uncertainty. Now, for those of you who are familiar with the decision tree, this is where I'm at a point where I have to make one of, say, three decisions: buy, sell, or hold. And I want to find the best of those three decisions. But after I make that decision, random stuff is going to happen. Maybe the price goes up or down and the customer has demands. And now I have the rest of the future. So the rest of the future depends on that first bit of randomness. Now, there's two things going on in this future. One is that max over pi. That Greek letter pi stands for policy, which means a method for making decisions. However, this pi means I need a rule for making decisions at every decision node in the future, and that policy has to tell me what to do. Then I have all sorts of forms of uncertainty, not just for one time period, for multiple time periods. I'm going to be honest, I don't really know very many problems where you can compute this exactly. So now we enter the world of approximations. So the first thing we can do is to say, hey, there's a piece of this function. I can roll this. This all depends on the state st+1 that I'm at in the future. What's the value of that state? And this has been studied for decades under the banner of Markov decision processes. Sadly, it's almost never computable. It's only computable for toy problems. So often what we do is we do approximations using machine learning. Okay, that's fine, but that expectation, I don't like to take expectations. In transportation logistics, the things that are random, it's not a coin flip or one random variable, it's thousands of random variables. I can't compute that, but there's a trick for getting around it. This is my book. This was my breakthrough that allowed me to tackle these truckload trucking problems. By the way, if you want to speak the language of the computer scientists, they call this Q learning, and they work with the Q factor. So don't ask me why, but they just have different notation. So I'm going to actually show you a trucking example that illustrates that math is actually useful. Here I have drivers that I have to assign to loads. The problem is I have to think about what's going to happen in the future. Now, what I'm going to do, now remember that future is uncertain. That's what we call a stochastic future. And that's really problematic. But what we're going to do is we're going to assign drivers to loads now, and then I'm going to approximate the value of drivers in the future. So if I send a Texas-based driver into Massachusetts, I'm going to have an estimate of the value of that driver. Now, this problem is actually quite easy to solve. I don't have any trouble solving this for thousands of drivers. We've actually done a test at 100,000. Now, here's an actual graph. This is the old graph that Schneider National originally used. I believe they still use it, but going back to 1980, where you have time and space. Now, here's a point in time where I have drivers and loads. Now I have the value of drivers in the future. Now, that graph behind, that's the graph that Schneider used, but they had to pretend that you knew the future, that you could go out 7 days and you knew what loads. We don't. What we're going to do is use an approximation of the future. Then we're going to simulate our way forward. Now we're going to do it over and over again. And every time I do it forward, I'm going to coin flip on anything that's random. Here is that logic being applied to 11 different trucking companies. And we see the profits steadily improving. After 15 iterations, we get anywhere from, say, a 10% to a 40% improvement, very dependent on the carrier. But this allows us to solve a series of small problems with an approximation of the future. Here's an actual animation from a major carrier. We are simulating every individual driver. We have his hours of service. We're looking at when the drivers need to get home. We're also trading off which loads are the most valuable. So we can handle a very high level detail when we do this. Now, I've covered 3 classes of policies, and I like to say, okay, what if none of those work? And when all else fails, we have to do what's called a direct look ahead. And direct look aheads are very common. There's a lot of times we have to think several moves in the future. But once I start thinking into a future with uncertainty, things get very complicated. So what we do is we create what's called an approximate look ahead model. Now, what I'm going to do is I have the same sequence of states, decisions, information. Notice I have tildes on everything. They all have 2 time indices. So I'm making a decision at time t, so everything is indexed by t, and I'm looking forward to time t prime. And there's a whole series of approximations I'll make. I'll approximate the uncertainty. I'm going to simplify the decisions that I make in the future. I'm going to limit my planning horizon. I may simplify my state variable. I may even simplify my decisions. So this is an art form that really depends on the problem. But let's imagine that I can do this and I can look forward, solve the problem, make a decision now, look forward, solve the decision, make a decision now. Once again, look forward, solve the problem, make a decision now. This is something all of us use. Google Maps. Let's imagine I'm in Hartford, Connecticut. I need to get back to Princeton. I'm leaving at 4 in the afternoon, and there's Google Maps saying, hey, I got this great trip, goes right through New York City. This is a deterministic look ahead. I'm not modeling uncertainty, rather Google Maps is not. Google Maps is taking a best point estimate and saying, wow, there's the best path. I'm sitting there going, Google, you can't possibly be doing this to me. New York, I'll be landing at New York City at 5 p.m. Maybe it's likely to be okay, but there's a risk that it might be very poor. This is what's known as robust optimization. And I can take sort of a worst case. I can take a 90th percentile and say, okay, I'd rather go around where it's a longer path, but less risk. There are entire fields of research, entire books on different ways to approximate that look ahead. Here's another problem that we've encountered at Optimal Dynamics. Shipper offers me a load on Friday, but today's Monday, and I have to say yes or no now. Do I accept or reject that load? Now, I don't even know where my drivers are going to be. Now, I can't do a point estimate. What we're going to do is 20 simulations into the future. I'm going to simulate dispatching 20 times, and I'm going to get 20 observations of whether I can cover that load. Now, let's say, in this particular example, that 18 out of 20 times I cover the load. I might be saying, that's good enough. If I have a 90% chance, I'll go in there and accept the load. This is real world data where we took a major carrier, took loads from the brokerage division, threw it at the fleet, 3,280 loads. The model said 20 out of 20 times, absolutely take it. 5,000 loads, it said not a chance. Don't go anywhere near this load, 0 probability. And then in between, anywhere from 5% to 95% probability, what we could do is go in and apply a simple rule. Well, if it's over 80%, I'm going to take it. Now, what I've just done is I have given you a tour through 4 classes of policies, the 2 under the policy search group and the 2 under look ahead. Now I'm going to claim These four classes of policies are universal. They cover any decision that you might make. And it covers decisions that you're already making. Any method you're using is already covered by this universal framework. So this is the ultimate toolbox. What it means is that I can go in, I could represent what you're doing now. I will always be able to solve a problem because these are very practical. All four policies in special cases can lead to optimal policies, but in the real world, we don't use that word optimal very much. We optimize, we do the best we can, but this is a universal framework, which means I can roll up my sleeves and go into any decision problem and approach it using these four classes of policies. Here's a little example, a fairly complex inventory problem that arises in energy storage. We created 5 variations of this problem, okay? Now, we created this with a certain idea in mind. Then I created 5 different policies. The first 4 are drawn from each of the 4 classes of policies, and the 5th one is a hybrid. And we were able to make each of these 5 policies work best on one of the data sets, which means you've got to understand all 5 classes. So this is not something that's well known, but I have pulled together everything I've seen in the academic literature, but also everything that I've seen in the real world. Guess what? I think there's some powerful policies out there that the academic literature has missed. Just because something's common sense doesn't mean it's bad. Now let's go back to our comparison with machine learning. So when I said, how do we design policies for decisions? So first of all, the first class of policies, the policy function approximations, consist of every mathematical function that we used in machine learning. The lookup tables, the parametric models, the non-parametric models. If I limited myself to just the PFAs when I'm making decisions, this would just be a different variation of machine learning, but I don't need a data set, I just need a model. The thing is, I don't have one class of policy, I have 4 of them, and the other 3 are all a form of optimization model. That is, each one of them is itself an optimization problem. I sort of have an optimization problem within my optimization problem. So this ultimately is the great unified framework with a path toward how to design and look for policies. Now, there's some complex trade-offs when you're designing policies between how hard it is to create the policy to represent a problem versus how hard is it to compute, because computation times are an issue. Now, there's a lot of blending here. I get endless questions about how do you choose among the 4 classes of policies. I've done my best to summarize this in various writings. If you go to this white paper that I put together for optimal dynamics, tinyurl.com/OD whitepaper, and it's only 13 pages, but even if you don't read any of it, just read the headings. You will see all 4 classes of policies. They're all there. You need all of them. Well, at least we need them all for work with optimal dynamics. This all has an intellectual foundation in my new book that'll be coming out, I believe, in May. It's already been submitted to Wiley, but this pulls all together all the theory. This is a technical book. This is for people who want to write code and put things on the computer. And moving forward, what I'm going to be working on is bringing the technical know-how here out to industry, putting it in plain English. So thank you very much. I've really enjoyed this. I hope you have too. I have more information on sequential decision analytics at tinyurl.com/SDA field. And the new book, even though it's not available yet, but you can download an early draft at tinyurl.com/RL&SO.